Hi everyone. In the previous lecture, we found the following things about the 2x2 determinants. The first thing is that it has this geometric interpretation in terms of the signed area of the parallelogram formed by the images of E1 and E2 under the transformation. The second thing is compatibility with multiplication. Determinant of A times B is determinant of A times determinant of B. We also saw that the determinant of the identity matrix is 1. And there were rules for row operations. One of them was that adding and subtracting multiples of one row from another doesn't change the determinant. Another was that multiplying a row by k changes the determinant by a factor of k. And then the last one is that swapping two rows changes the determinant by a factor of -1. These properties really do allow us to generalize the determinant to n by n matrices. In particular, the property of the determinant of the identity matrix being 1 plus the rules for row operations together can be taken as the definition of the n by n determinant. From that definition, we'll be able to derive the property that the determinant of A times B is the determinant of A times the determinant of B, and we'll be able to get a geometric interpretation from it. But first, let's go through an example where we use this definition to compute the determinant of a 3x3 matrix. The process is similar to what we did in the 2x2 case, and so because this is kind of the second time around, we can write out the calculations in a little more of a streamlined way. And so one thing that helps with that is this notation with the vertical lines that look like absolute value signs. That is just shorthand for the determinant. And so the idea is that we can do row operations on the matrix, and at each step we can write down an equation that relates the determinant on the left-hand side to the determinant on the right-hand side. So in this case, the first row operation we want to do is to subtract 2/3 times row 1 from row 2. So I've written the result here, but the important thing is that this row operation, where you subtract a multiple of one row from another row, doesn't change the determinant. That's one of the rules. And so that equal sign is there because those two determinants are actually equal. So the next step would be to do row 3 minus 5/3 times row 2. So here's what you get when you do that, and again, the determinant doesn't change when you do that row operation. At this point, we could multiply each row by a scalar in order to make the pivots equal to 1. Now, these operations do change the determinant, and so we need to introduce factors to compensate. When you divide row 1 by 3, that divides the determinant by 3, and so we have to multiply back by 3 to compensate. Same thing when you divide row 2 by 3, and then when you multiply row 3 by 9, that multiplies the determinant by 9, and so we have to divide by 9 to compensate. In this case, we're kind of lucky that all three of these things cancel out, but that's just a coincidence that happened with this particular matrix. And then finally, we would want to use row 3 to eliminate the entries above the pivot in the third column. And again, this is an operation that doesn't change the determinant. And finally, we have the identity matrix, which we know the determinant of the identity matrix is 1. And so that's the final answer. The determinant that we wanted to compute is 1. So one thing I'll point out is that there's a little shortcut we could have used here. In the middle step of this calculation, we had a matrix that was upper triangular, in the sense that all of the entries below the diagonal were 0. There's a fact that the determinant of a triangular matrix is just the product of the diagonal entries. So in this case, it would be 3 times 3 times 1/9, which is equal to 1. And actually, if you look at what happened in the rest of the calculations, you can see why that's true. We effectively pulled out the 3 and the 3 and the 1/9 in the next step. And then in the following step, we used an operation that doesn't change the determinant to produce the identity matrix. This sort of thing is what would always happen once the matrix is triangular, and that's why the shortcut is valid. Okay, now there is another method for computing determinants, which I probably should tell you about because it's actually the way that they would teach you to do it in an engineering or a physics class, and it's called cofactor expansion. And the way this works is that you can pick any row or any column of the matrix and do an expansion along the entries of that row. So to illustrate it, let's say that we're going to use the first row of this matrix to do an expansion. Well, the first entry of that row is 3, and so what you're supposed to do is take that 3 and multiply by the determinant of the 2 by 2 matrix that you get when you block off the row and column that 3 is in. So that's 3, 2, 5, minus 1. And then you do the same thing for the next entry in the row. In this case, that's the 0, and you block off the same row and column that the 0 is in, and the 2 by 2 matrix formed out of the remaining numbers is 2, 2, 0, minus 1. Now notice that there's a minus sign here. This minus sign is part of the cofactor expansion formula. I'll talk a little bit more about the signs later, but the reason it's there is that it's part of the formula. Of course, in this case, there's a 0, so it doesn't matter whether it's plus or minus, but in general, it's important to know that that sign is there. And then for the last term, you would take the 4, which is the last entry in the row, block off its row and column, and the 2 by 2 matrix that you're left with is 2, 3, 0, 5. And so now you can compute these 2 by 2 determinants using the AD minus BC formula. And the first one has determinant minus 13. The second one we don't actually need to calculate because you're multiplying it times 0 anyway. And the third one has determinant 10. And so we get minus 39 plus 40, which is equal to 1. Okay, so back to this question that you probably have about why the middle term had a minus sign but the other two terms didn't. The reason for that is that the cofactor expansion formula uses something that's called a sign matrix. To make the sign matrix, you put a plus sign in the upper left, and then you use a checkerboard pattern of pluses and minuses to fill out the rest of the matrix. This is the rule for which entries get a plus sign and which entries get a minus sign. So for example, if you were to do a cofactor expansion across the middle row of the matrix, you would have minus 2 times the determinant of 0, 4, 5, minus 1, plus 3 times the determinant of 3, 4, 0, minus 1, and minus 2 times the determinant of 3, 0, 0, 5. And probably you should pause and do these calculations for yourself, but you get minus 20 for the first 2 by 2, you get minus 3 for the second one, and you get 15 for the third one. And so the end result is 40 minus 9 minus 30, which is 1. So you can see that it worked. Cofactor expansion also works for larger matrices. For example, here's a 4 by 4 matrix. And the way to use cofactor expansion to your advantage is to pick a row or a column that has a lot of zeros. So in this case, the best option is going to be the third row. And just for your reference, this is what the 4 by 4 sign matrix looks like. So that 2 in the third row would get a plus sign. So you'd have 2 times the 3 by 3 matrix that you get when you block off the row and the column that the 2 is in. And so that's here. And all the other terms in this expansion are going to be 0 because the other entries in this row are 0. So this is all there is. And now we've got a 3 by 3 matrix where we can do a cofactor expansion for that. And in this case, the first row would be the best option for that. Since that 5 is the only non-zero entry in the first row, that's going to give you the only non-zero term in the cofactor expansion. And so you just have 5 times the determinant of 7, 2, 3, 1. And when you use the AD minus BC formula on that, you just get 1. So the result is 2 times 5 times 1, so that's 10. So that's how the cofactor expansion method works. It takes some practice to get used to, but it's a straightforward process, and so once you get the hang of it, it'll feel pretty easy to you. You will notice that I didn't actually prove that the cofactor expansion gives you the same result as the row operation method. There's actually a lot of work involved in doing that proof, and it's not worth our time. But you can take for granted that you would actually get the same answer either way. So then the question is, which method should you use? Which one is better? Well, for n by n matrices, the cofactor expansion method requires about n factorial multiplications. And you can see this because you have to do 2 multiplications to do a 2 by 2 determinant. And then for a 3 by 3 determinant, you would do 3 2 by 2 determinants and multiply each one times a cofactor. And then for a 4 by 4 determinant, you would have to do 4 3 by 3 determinants, and so on. Although it is worth pointing out that, as we saw in the example above, you don't have to do all of those calculations if your matrix has enough zeros. And so in general, the cofactor method can be quite good if your matrix has lots of zeros. So in comparison, for n by n matrices, the row operation method requires about n cubed multiplications. And so when you compare n factorial to n cubed, you'll see that for 3 by 3, 4 by 4, and maybe even 5 by 5, especially if there are zeros you can take advantage of, the cofactor expansion method is going to be quicker. And the truth is that these are the ones that you're going to be doing by hand. And so that's why cofactor expansion is the method that they teach you for the engineering and physics classes. But what if you had a 30 by 30 matrix? If you used row operation method for this, then you'd have to do 30 cubed calculations, which is 27,000. You obviously wouldn't want to do that by hand, but for a computer, that's nothing. Now suppose you use the cofactor method for your 30 by 30 matrix. Then the number of operations would be about 30 factorial. And 30 factorial is approximately 2.65 times 10 to the 32, which is a lot bigger than 27,000. And just to give you an idea of how much bigger it is, let's suppose that you used the world's fastest supercomputer to do this calculation. As of right now, in 2020, the world's fastest supercomputer is in Japan, and it can do 415 quadrillion computations per second, which is a lot. If you used that computer to calculate a 30 by 30 determinant using cofactor expansions, it would take 20 million years. So the moral is that for small matrices, the cofactor method is better, but as matrices get larger, the row operations method becomes better, and it becomes better in a very dramatic way. To the point where, for practical purposes, cofactor expansion doesn't work for large matrices unless most of the entries are equal to 0. All right, so far we've just talked about how to calculate the determinant, and so I want to follow up on what does it actually mean. The geometric interpretation of the derivative is really just a higher dimensional version of what we saw in the two-dimensional case. So here I'm drawing three-dimensional pictures because that's as far as my artistic capacity will allow, but you can try to imagine how it would work in higher dimensions as well. So the idea is that you've got the E1, E2, and E3 vectors, which determine the 1 by 1 by 1 unit square. And then you can look at the images of those three vectors after you multiply by A, and those three vectors will determine a parallelepiped. And then the result is that the volume of that parallelepiped is the absolute value of the determinant of A. It would take a little bit too long for me to go through the details about why that's true, but basically it comes from the rules that we use to define the determinant and thinking about those rules in terms of elementary matrices. In particular, if A is the identity matrix, then the parallelepiped would just be the unit cube, which has volume 1. If A is an elementary matrix that corresponds to adding or subtracting a multiple of one row to another, then that's actually a shear transformation, and the result would be a parallelepiped that would have the same length, width, and height as the unit cube, 1 times 1 times 1, and so the volume would be 1. If A is the elementary matrix that corresponds to multiplying a row by k, then, at least if k is positive, the parallelepiped would be a rectangular box with dimensions 1 by 1 by k, and so the volume would be k. And then if A is the elementary matrix that swaps two of the rows, then you would still have the unit cube with just two of the vectors swapped, and so the volume would be 1. So basically the idea is that when you compute the determinant of A using row operations, you're breaking A up into elementary matrices, and you're keeping track of how the volume changes at every step of the process. But what about the sign of the determinant? Well, there's a general word for what it is that the sign of the determinant tells you, and that word is orientation. So what is orientation? Well, the geometric meaning of it is actually different in every dimension. We saw in 2 dimensions that orientation told us the difference between clockwise and counterclockwise. If a 2 by 2 matrix has negative determinant, that means that it turns clockwise arrows into counterclockwise arrows, and vice versa. In 3 dimensions, a good way to think about orientation is right hands versus left hands. If the determinant of A is negative, then that means that A would transform a right hand into a left hand, and vice versa. And so if you remember the demonstration that I asked you to do in 2 dimensions, where you draw a counterclockwise arrow on paper, flip the paper over, and see that it's a clockwise arrow, the corresponding demonstration in 3 dimensions is to stand in front of a mirror and hold your right hand up and see that it looks like a left hand. Now, when we draw 3-dimensional pictures, There's a conventional way to do it, which is that you draw your axes in a way which follows something that's called the right-hand rule. And the way that works is as follows, and you'll have to do this with me. Take your right hand, point your fingers in the direction of the E1 vector, curl your fingers in the direction of the E2 vector, and you'll see that your thumb is pointing in the direction of the E3 vector. That relationship is the right-hand rule. The right-hand rule plays the role in 3 dimensions that the counterclockwise arrow played in 2 dimensions. And so the sign of the determinant tells us whether that relationship still holds in the image. If the images of E1, E2, and E3 satisfy the right-hand rule, then the determinant of A will be positive. And so, for example, in the picture that's at the top of the slide right now, that's an example of a matrix where the determinant would be negative. And the way to see that is you take your fingers on your right hand and point them in the direction of the orange vector, curl them in the direction of the green vector, and you'll notice that your thumb is pointing away from the blue vector. And so it's not satisfying the right-hand rule. The determinant is negative. All right, I'll finish this lecture with a couple of important facts about the determinant. So the first thing is that the determinant of A times B is equal to the determinant of A times the determinant of B. We saw this in the 2x2 case, and it's still true for higher dimensional matrices. Conceptually, the explanation is similar to the 2x2 case, where you can think in terms of scaling of volumes instead of scaling of areas. But algebraically, this fact can be proven directly from the rules that we used to define the determinant. And the idea there is that these rules, even though they're not phrased in exactly this way, you could reinterpret the rules as saying that the way to compute a determinant is to factor the matrix as a product of elementary matrices, and then multiply the determinants of all of those elementary matrices, where those determinants of the elementary matrices are given by the rules. And so the fact that the determinant of AB is equal to the determinant of A times the determinant of B comes from the fact that if you factor A as a product of elementary matrices, and then you factor B as a product of elementary matrices, then you can multiply those 2 factorizations together to get a factorization of AB as a product of elementary matrices. And I know that what I just said isn't super easy to understand, and that's okay, as long as you're willing to believe that this equation is true. And then the other important fact is that the determinant of A is non-zero if and only if A is invertible. And basically the reason for this is that invertible matrices are ones where the reduced echelon form is equal to the identity. So as you're doing the row operations and keeping track of how the determinant changes, either you eventually get to the identity matrix, in which case that determinant is 1, or you'll get a row of all zeros. And once you get a row of all zeros, then you can conclude that the determinant is 0. But this is also something that's worth thinking about from a geometric point of view. I'll let you do that as an exercise. But basically, to summarize, if you know how to compute determinants in 2 ways, using row operations and using the cofactor expansion method, and if you remember these important facts, then that's basically everything you need to know about determinants.